In this video, we'll take a look at double and half angle identities. So a general note for double angle formulas. The double angle formulas are as follows. The sine of 2 times an angle is equal to 2 times the sine of an angle times the cosine of that angle. So I included a proof of where that comes from. Again, identities are built from other identities. So if you take our sine sum identity, the sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta, and make those the same angle. The sine of theta plus theta equals sine times the cosine theta plus cosine sine theta. Add the two like terms together, we create a new identity. The sine of 2 times the angle is equal to 2 times the sine times the cosine of the angle. So the cosine identity and the tangent identity for double angle can be created very similarly. So what we're going to take a look at is, what do we use these double angle formulas for? So one of the things we use them for is to find exact values and then of more angles on the unit circle, and also to find values given a sine, cosine, or tangent of an angle. We can find the sine, cosine, tangent of all the double angles. So our first example is using a double angle formula to find the exact value involving tangent. So if we're given that the tangent of the angle is equal to -3/4 and the angle is in quadrant 2, to find the following: the sine, the cosine, and the tangent of the double angle. So we don't have to find the angle exactly. What we do is we use the identities to find sine, cosine, and tangent. And notice the identities use sines and cosines, okay, except for the tangent identity, but sines and cosines. So what we have to find is the sine and cosine given the tangent. So we've done this before, is to draw your angle, draw a triangle to reflect the given information. We're given that our angle is in quadrant 2, so our angle is here in quadrant 2. So what we do is draw our reference angle and use a reference triangle. If we know that the tangent is -3/4, the tangent of an angle is equal to the opposite over adjacent. So the opposite side is equal to, let's see, we have -3/4. That's going to be negative, or I'm sorry, the opposite side over the adjacent side. That's going to be, the opposite side is 3, the adjacent side is 4, and adjacent side is negative because in that second quadrant, the x values are negative, y values are positive. Then find the hypotenuse. So in this right triangle with opposite side 3, adjacent side -4, we take 3 squared plus -4 squared is equal to the hypotenuse squared, 25, square root both sides, and we end up with a hypotenuse equal to 5. So in our second quadrant, we have a reference triangle with side lengths 3, -4, and 5. And then I just want to show that the tangent is in the second quadrant, the angle. That means our angle is between 90 degrees and 180 degrees. So if we're finding a double angle, if we double 90, 2 times 90 is 180. 2 times 180 is 360. Then our angles are going to be between 180 and 360, okay? So let's go ahead and substitute the values into double angles. Okay, so I found the 3 side lengths. I'm now going to find the sine of the angle is equal to the opposite over hypotenuse. So in this case, opposite over hypotenuse would be 3/5, and it's positive in the second quadrant. Cosine of the angle is adjacent over hypotenuse, which would be -4/5. So we're using these values, positive, negative values, and then we'll end up with the correct sine of our double angle. So the sine of 2 times the angle is 2 times the sine times the cosine. So we substitute our values in for sine, which is 3/5, and cosine, which is -4/5. And we end up with 2 times 3 is 6 times 4, negative 24 over 25. Next, we take a look at cosine. We have 3 different possibilities, so you can use any one of the 3. If you want to just use the first one, cosine squared minus the sine squared of our angle. We put cosine, which is negative 4/5 squared, minus the sine, which is 3/5 squared. We get positive 16 over 25 minus, let's see, 9/25, and we end up with 7 over 25. So the cosine of 2 times the angle is 7 over 25. For tangent, you can substitute your value into the tangent, and so we would get 2 times the tangent was given in the problem as negative 3/4 over 1 minus negative 3/4 squared. We get 2 times negative 3/4 is a negative 6/4 divided by 1 minus 3/4 squared is 9/16. So I get negative 6/4 divided by 1 minus 9/16 is 7/16. Divide means to invert and multiply. Negative 6/4 times 7/16, 16/7. Let's see, I should reduce my fraction. 3, 2, 2 goes in here, 8, and I end up with negative 24 over 7. Probably an easier way, though, for tangent 2 theta is to use that's the sine 2 theta divided by the cosine. You'll get the same answer either way. But if we use sine divided by cosine, we have negative 24 over 25 divided by 7/25, which equals negative 24/7. So once you have sine and cosine, you can divide those to get tangent. All right, so that's double angle. The next identities we'll look at, let me look at one more example. If sine is equal to 7/8 and x is in the second quadrant, determine exact values of each of the following. So if your sine of x is 7/8, you can find the cosine by using your, let's go ahead and draw a triangle. It'll be in the second quadrant. So you're going to use the reference triangle again. Sine is 7 over 8, that's opposite over hypotenuse. And then you would use Pythagorean theorem to get this other side. So you would take 8 squared minus 7 squared is equal to that length squared, let's call it x. 64 minus 49. 64 minus 49 is 15. Square root both sides. So this length, we would use negative square root of 15 because it's in the second quadrant. So now that you know the sine of x is 7/8, the cosine of your angle would be adjacent over hypotenuse, negative square root of 15 over 8, and the tangent is equal to opposite over adjacent, negative 7 over the square root of 15. Rationalize your denominator. We get negative 7 square root of 15 over 15. Then use your values for sine, cosine, and tangent in the double angle. So the technique is the same. Go ahead and use that triangle, the reference triangle, to find your other values. All right, next part is called half-angle formulas. Half-angle formulas are what if you're taking your angle and dividing by 2. So again, identities are derived from other identities. We're not going to do the proofs here, but that's where these came from. So there's a plus and a minus in front of each of these. So we have to determine whether it's positive or negative depending on what quadrant we're in. So let's take a look at an example. Using a half-angle formula to find the exact value of a sine function. So notice that these are all in terms of sines and cosines. Sine and cosine are in terms of cosine only. Tangents in terms of cosine only, or there are actually 3 variations of it. So if you want to find the sine of 15 degrees using a half angle formula, sine of 15 degrees is not a value we have on our unit circle, but the sine of 15 degrees is the same as the sine of 30 degrees divided by 2. So if you use the formula sine 30 divided by 2, you get plus or minus. Say 15 degrees is in the first quadrant, so it's going to be positive. So we get square root of 1 minus cosine 30 degrees over 2. So you go to your unit circle and substitute cosine of 30 degrees. So on the unit circle, 30 degrees is pi over 6. Cosine is square root of 3 over 2. So we get the square root of 1 minus the square root of 3 over 2 over 2. And then now we simplify the inside. So this is a complex fraction. Something that will make this simplification a little easier is to find the fraction and multiply the numerator and denominator by the common denominator. The only fraction we have within each of these individual terms is 2. So I'm going to multiply the numerator and the denominator by 2. And that's going to give me a simplified, not a complex fraction. So if I multiply 2, I get 2 minus square root of 3 over 2 times 2 is the square root of 3 over 2 times 2 is 4. So that is the exact value of the sine of 15 degrees. So you can use the half angle formulas to find more exact values of each half of angle measure of any of the items on the unit circle. All right, last example is what if you know the sine of an angle equal to 4/9 and it's in the third quadrant? Determine the exact value of each of the following. Use fractions and radicals only, no decimals. And we don't need to rationalize the denominator. All right, so we're given the sine and that it's in quadrant 3. So we draw our triangle, reference angle. Our angle is going to end up in quadrant 3. So our reference triangle is here. So this would be our reference angle. The sine is equal to the opposite over hypotenuse. So opposite would have length 4, hypotenuse 9. Now we're in the third quadrant, so the x and y values are negative, so that would be a negative 4. And we want to find that third side. So use Pythagorean theorem. We get 9 squared minus 4 squared is equal to x squared. 81 minus 16. 81 minus 16 is 65. Square root both sides. So we have this length as negative square root of 65. All right. And can 65 be simplified? 65 divided by 5 is 13. So we can't simplify that radical. All right, so we want to determine sine of x over 2. The sine of alpha over 2, we have to figure out whether it's positive or negative. So if it's in quadrant 3, then your angle is somewhere between 180 degrees and 270 degrees. So if we're finding our angle divided by 2, then our angle is somewhere between 90 and 270 divided by 2, which is 135. So somewhere between 90 and 135 degrees means it's going to land in the second quadrant. So that means our sine is the y value is going to be positive, cosine as the x value is going to be negative, and tangent will be negative because it's sine divided by cosine. So determine your sines up front, and then it makes it a little easier. So now we can find our sine cosine of the half angle. So for the half angle, we need the cosine only. So the cosine of alpha, cosine of our angle, is equal to adjacent over hypotenuse, so that would be negative square root of 65 over 9. So the sine alpha over 2, in our case x over 2, is going to be positive square root of 1 minus the cosine, which is negative square root of 65 over 9, over 2. And then we're going to go ahead and simplify our fraction. Multiply numerator and denominator by 9. We get 9 square root of 9 plus the square root of 65 over 2. So that's our sine. For the cosine, we do the same thing, except we have 1 plus. Negative 6 square root of 65 over 9 over 2. So when we multiply numerator and denominator by 9, this time we get 9 minus the square root of 65 over 2. And since our cosine is between 90 and 135 degrees, it's negative. And last, the tangent. You can use any one of the three formulas. It doesn't matter which. I'll just pick the second one. Sine, which is given in the problem. So the sine was negative 4/9 divided by 1 plus the cosine, divided by 1 plus negative square root of 65 over 9. So 9 is the common denominator. Multiply the numerator and denominator by 9 to simplify your complex fraction. And we end up with negative 4 in the numerator. Looks like a 9. Negative 4 in the numerator over 9 minus the square root of 65. So we go back up. It's negative. So if you put a negative in front of this, it's going to make that 4 positive. So I'm going to end up with 4 over 9 minus the square root of 65. And at the beginning it said no need to rationalize your denominator, so we can leave it just like that.